All right. Hello, everyone. Hoping you had a good holiday. Sorry that I can't be there for the next couple of weeks. But hopefully the tutorials that I'm putting up here give you a good overview of these couple of chapters on solubility and in terms of concentration. So I'm putting these up here so that you can basically watch the videos as kind of your homework, and then you can do the questions whenever you want to be doing them. So you'll have time in class to be doing it. If you want to kind of flip it over and do it the other way around at home, then that's fine as well. So while you're watching these, have a think about whether this is something that you think would be useful moving forward as well. So I know that some schools like to have basically all of their lessons done like this. So I put this up on YouTube, and then you'd watch that at home. You come in, and then you do the questions there with me helping you, as opposed to me teaching the class at school, and then you going home and doing questions at home. Have a think about which of those you think would be more useful for you. Do you prefer what we've been doing so far, or would you prefer me to make more of these and then kind of teach it in this flipped classroom style a bit more? All right, so let's make a start here. So for this lesson, we're going to talk about different solubilities and kind of start talking a bit more about the quantitative aspect of solubility. So this is going to be useful for your upcoming research task as well. So you'll be doing an investigation where you have to come up with the method, and then you'll do the investigation and write up all your results onto a poster to disseminate, so to share your results with other people. So this is a good one to be paying attention to. Well, all of them are, but this one in particular. All right. So far we've been looking at solubility just in terms of looking at that solubility table, which in terms of ionic compounds, which basically just says, well, is it soluble or is it insoluble? We've also had that column sometimes that says slightly soluble, which is kind of weird. Like, does that mean it's soluble? Does that mean it's not soluble? So really what we've got going on here is that solubility is a spectrum. It's a value that we have for something. And whether we say something soluble or insoluble is basically just saying it's very soluble or it's not very soluble. It's kind of like temperature. We can say something's hot or we can say something's cold. But then if you have something that's 30 degrees, is that hot or not? Well, it depends on what you're comparing it to. It's more useful to give temperature a numerical value, and then everyone knows exactly what you're talking about. And we can kind of do the same thing with solubility. So something's insoluble is basically going to have you're basically barely going to be able to dissolve any of it. Something that's soluble, you're going to be able to dissolve a lot. And we'll look at the specific values in a bit. So as an example, sodium chloride, so table salt, and your sugar, so sucrose, are both really soluble in water, but sucrose can actually dissolve a lot more, even though they're both soluble. So they have different values of solubility, even though they would both fit into the soluble category. So just a couple of examples here. So calcium hydroxide is one of those compounds that fits into the slightly soluble section. So you can dissolve 1.7 grams of that in a liter of water at room temperature, versus sucrose, which we know can hydrogen bond with water, has lots of OH groups. So you can fit kilograms of that in a single liter because it's so soluble. So in terms of what our learning intentions are here, so I'd like you to be able to understand the use of solubility tables and experimental measurement of solubility. So we're going to look at some different concentration units in the next PowerPoint, but for this one, we're just going to be talking about grams per 100 grams of water. You should be able to understand the quantitative relationship between temperature. So basically, I'm just saying here, it's when you increase the temperature, what happens to the solubility of a solid, what happens to the solubility of a liquid, what happens to the solubility of a gas. And you should be able to understand using solubility curves. The curriculum specifies this predictive tool in selected biological, domestic, or industrial contexts. Basically, you just need to be able to read a solubility curve. So to break that down, technically part of this is being able to use the solubility table. We have already talked about that a bit though, so hopefully you can remember that from before the holidays. Here we've got explain the effect of temperature on solubility of solids and gases. And the main thing that we'll be doing here is reading solubility curves. And then we'll be able to figure out whether a solution is saturated, unsaturated, or supersaturated from that curve there. All right. So let's make a start. So we said that solubility is when we're looking at the quantitative, we can look at solubility quantitatively in terms of a number. So the main way we'll look at it for now is in terms of grams per a certain mass of solvent. Now remember, this semester is all about water, so we're looking at dissolving things in water. And the unit that we typically use here, and you'll see on most of the solubility curves, is grams per 100 grams of water. So you'll see it as written like this. So it's saying if you had 100 grams of water, remember that that's basically 100 mils. If you have 100 grams of water, how many grams are there? So if something is 5 grams per 100 grams of water, where we can say, well, if we've got 100 grams of water, there'd be 5 grams in it. You could dissolve 5 grams in it. If you had 200 grams of water, you could dissolve 10 grams of the thing in it, etc. And so there's kind of these rough cutoffs in terms of saying whether we can say something's soluble, insoluble, or slightly soluble. So if the solubility of something is more than 1 gram in 100 grams, then we'd say it's soluble. So if you can dissolve 3 grams of something in 100 grams, then we call it soluble. If it's between the 0.1 and 1 gram per 100 grams of solvent, we call it slightly soluble, and anything that's less than that we call insoluble. So you don't need to memorize these or anything like that. You just need to know, I just like you to be aware of the fact that when you're looking at that table, which I'll give you for the tests and exam or whatever, wherever you need it, when you're looking at that table that we looked at last time, when you're looking at the soluble, insoluble, slightly soluble, it's basically saying that compound is within that solubility range, these ranges that we have here. You don't need to, I'm not going to give you 0.75 grams per 100 grams and ask you how soluble it is. All right, so when we dissolve things, we can describe things, a solution, in a few different ways. So remember that solubility is going to tell you the maximum amount that a solution can hold. You can always dissolve less than that amount. It doesn't mean that it magically always gets to that amount. If you can dissolve 5 grams per 100 grams of a solvent, so if the solubility of something is 5 grams per 100 grams, you can still dissolve 3 grams per 100 grams. That also works. It's under that threshold. The more important thing here is that if you then tried to put 6 grams in per 100 grams of water, so say you've got 100 mils of water, you put 6 grams of your solute in, we'd find that only 5 grams of it would dissolve. And then 1 gram would just sit at the bottom of your beaker. Or not dissolve. So depending on whether we're kind of at this threshold, so in this case here, we could either dissolve 5 grams in it. We could say we can put that much in it. We could not be quite at that point, or there are a couple ways we can be above that point as well. We have 3 different names for that. So if we're sitting, if we've dissolved the maximum amount of solute that we can get in there, so if we've got 5 grams per 100 grams, if we've dissolved enough that it can't hold any more, then we say it's saturated. Just like when we were talking about organic compounds, an organic compound is saturated because it can't hold any more hydrogens. In the case of a solution, it's saturated because it can't hold any more of the solute. So that doesn't mean that you've put the exact right amount of solute in. In our example here where we put 6 grams in, it's still saturated because it's full. It's holding this 5 grams per 100 grams there. Even if there's excess, it's still a saturated solution. So an unsaturated solution is just something where we have less than that maximum mass. So in this case here, if we try and dissolve 3 grams per 100 grams, it'll all dissolve, but it'll be unsaturated. We could dissolve more of it in there. And the last one is supersaturated. So I've got a link one here. If you want to follow that through on the PowerPoint, you can read about some examples of where we use these solutions. But a supersaturated solution is where somehow we've managed to dissolve more than what is normally capable of dissolving in this solution. So if we if, for example, here we had 6 grams per 100 grams, but we managed to make it so that all 6 grams dissolve. So it managed to actually be 6 grams per 100 grams, whereas remember this one of those grams didn't dissolve. If we managed to get it so that all of it dissolved, it would be a supersaturated solution. So this normally happens when we have something that's heated up, and then we cool it back down, but we don't give it the ability to form crystals. So we'll see in a bit how that works as well. The main usage of these is in like hand warmers and cold packs and things like that. So I've got an example here. So this is a supersaturated solution. Normally, you can see at the start, most of the solution is not actually reacting. So it starts at here, all of this here isn't reacting. What's actually kickstarted this reaction is that someone's dropped in a little seed crystal on that. So the process of the solute precipitating out. So basically all of the excess solute here is going to come out and turn into this white crystal. But that's only going to start if the solute has somewhere that it can actually grow on, if it can become a solid. So we're not really going to get into crystal dynamics here. But suffice to say, for something to go from a dissolved state into the solid state, it needs to have something to grow onto. You can't just have a sodium ion sitting there by itself and then it decides that it wants to be a solid. It needs to actually join up to other sodium and chloride ions before it can crystallize. And as often this happens naturally, but there are certain ways you can stop it from happening, which gives you these supersaturated solutions, which are pretty cool. So this process, often we use this as a way to have a reaction that releases heat or sucks in heat to control a temperature at some point, because the reaction is normally has a pretty significant change in heat. All right, so in terms of solubility, we're mostly going to talk about solids here because we've been talking about ionic compounds, as you don't really have gaseous ionic compounds. Talk a little bit about solubility of liquids and gases later, but for now the most important one is solids. And for that, as we increase temperature, we're going to increase the amount that's able to dissolve in it. So as temperature increases, solubility is also going to increase. So now there isn't a specific mathematical relationship that we can look at here for all ionic compounds. We're going to end up with a different graph for each compound depending on the exact effects, exact ionic effects between ions and the solvent and things like that. So you don't need to figure out anything like that. Basically, if I'm going to ask you a quantitative question about solubility, you'll be given a graph. So we've got a nice one here. You can see we've got lots of funky things here. We've got some exponential ones, we've got some linear ones. The main thing here is that you just need to be able to look at one of these and be able to read some values off of it. So one of the main things we can do with our graph here, so we call this a solubility curve, is that we can figure out what type of solution we have. So if we're looking, let's say we're looking at potassium chloride. So it's this line here. And we've got a solution of potassium chloride and it's at room temperature. So 25 degrees here, standard laboratory conditions. So when we want to look at, how much we can dissolve in it, all we do is we follow that line up, just like you're reading any graph. That was great. Up to about here. And then we'll follow it across and read off the y-axis. So what have we got there? We've got that's about 34. Yep. So let's say that can hold 34 grams per 100 grams there because that's our unit on the y-axis. All right. So when we're looking at solutions, if the mass of the solute that's dissolved puts it below that line, then it's going to be unsaturated. So if I said I've got 25 grams per 100 gram solution of potassium chloride, you could go, all right, it's 25 grams at 25. Okay, is this point here above or below this point here? Or you could say it's below it, so therefore it's going to be unsaturated. And if we're looking at this here, this whole area below the blue line is unsaturated. It's getting a bit messy there. If it's on the line, it's going to be saturated. So if we have exactly 34 grams per 100 grams of water, then it's going to be saturated. And you can probably guess what it is if it's over the line. If it's over the line, it's super saturated. So say if we had 40 grams per 100 grams, so 40 at 25 degrees, it's above our potassium chloride line. So therefore, we'd say it's supersaturated. So we can use this to answer some different problems like this. So we can use our curves to figure out solubilities, and we can figure out whether things are saturated, unsaturated, supersaturated. So let's have a couple of worked examples, and then you can have a go at some. So we've got our first question here: what mass of sodium nitrate, remember NO3 is nitrate, will dissolve in 100 grams of 10-degree water? So we're at 10 degrees. So let's go up until we hit sodium nitrate. Sodium nitrate's all the way up here. So we know that 80 grams can dissolve in 100 grams of 10-degree water. How much water do we have? Well, we've got 100 grams. So if there's 80 grams in 100 grams, then the answer to this, the amount that's in 100 grams, must be 80 grams. So we can dissolve 80 grams of sodium nitrate in there. At what temperature will 25 grams of potassium chlorate dissolve in 50 grams of water? All right, so how much do we have dissolved per 100 grams of water here? So if we've got 25 grams per 50 grams of water, then per 100 grams, we'd have 50, right? Like if you had 20 grams in one glass of water, then it would make sense that if you had 2 glasses of water, you have 40 grams. So if we know how much is in 50, then we can figure out how much is in 100. It's just this kind of 1 to 2 ratio here, right? Which then is exactly what is written as our unit here. So if you get something where there's an amount of water that's not 100, you will need to convert it to grams per 100 grams of water to make it work for the solubility curve. So we're looking at when will potassium chlorate, so it's this one here, when will it be able to hold 50 grams per 100 grams? So take this one here, fold across, go down, and we're probably looking at 93 degrees or something like that. Now, I'm not expecting you to be like mechanical and know exactly that's 92.5 or something like that. Something that's within a couple of degrees here is fine. If you wanted to do something accurately, I would just get you to do it on Excel. All right, so let's have a look at the saturation level of these ones here. So we've got 20 grams of sodium chloride in 200 grams of 5-degree water. So let's make sure that this is in per 100 grams of water first. If there's 20 grams in 200 grams, we know there'd be 10 grams in 100 grams. So we're down here. We're in 5-degree water, so we're here, and we can compare that to our sodium chloride curve. And we can see that it's much lower than that. So if it's lower than the curve, it's unsaturated. All right, next up, we've got 30 grams of potassium dichromate in 100 grams of 50-degree water. Well, that's already in grams per 100 grams. So we're at 30, we're at 50 degrees. How does that compare to the potassium dichromate line? Well, it's exactly on it. So this is going to be saturated. And our last one here, we've got 35 grams of potassium nitrate in 50 grams of water. So 35 grams in 50 grams is the same as saying that there's 70 grams in 100 grams. So we'll go 70, and we're in 40-degree water. So I'll go across, let me rub those out. 70 grams in 40-degree water. So we're over here. We can say, well, how does that compare to our line, which is here? Well, our point here is above our line here, so therefore it's supersaturated. There we go. So with those, and you can rewind if you want to have a look at those again, with those you should be able to work through the 14.1 questions in the textbook there. So you can pause the video, go work through those, and then we'll work on the next section. All right. So next up, we're briefly going to talk about crystallization. So we're not going to go too much into this. This is actually a really useful thing that we use a lot in organic chemistry. So we dissolve things and we recrystallize them to purify things and things like that. So we get crystallization happening when a solution cools, so that basically a solution that was saturated is now supersaturated. The solution will normally, unless you've done it in a specific way to make it supersaturated, will normally make crystals until this till the concentration goes back down to a saturated level. So if we look at our curve here, so let's take an example. Let's take the potassium chlorate here. So if we had a saturated solution of potassium chlorate, pen's not doing great there. If we had a saturated solution of potassium chlorate at 70 degrees, for example, it'd have 30 grams per 100 grams. So let's say you've got 100 grams of water, there's 30 grams dissolved in it. And then let's say you cool it down until it goes to room temperature. And it comes down to here, so it can hold about, what's that, 9 grams. So we can see if the solubility is decreased from 30 grams down to 9 grams, then 21 of those grams must have left the solution and turned into a solid. So we would end up with 21 grams of it turn into a crystal coming out of the solution as a solid. So the main thing here is that the mass of crystals that's going to form is going to be equal to the difference in the mass of the dissolved solute between the two temperatures, which is what we just saw. So that difference in those Y values between the two temperatures. So we've got our curve here. Let's have a look at another one. So what mass of sodium chloride crystals will form if we've got 100 mils of a saturated sodium chloride solution at 80 degrees and we cool it down to 20 degrees. So 80 degrees, it can hold 39 grams per 100 mils, per 100 grams. Remember, mils and grams are pretty interchangeable with water. So 39 grams here, all right? And when we cool it down to 20, it can hold 35 grams. So we'd expect there to be 39 minus 35 is going to be 4 grams of difference there. So we'd expect 4 grams of sodium chloride crystals to come out of solution there. All right. And a couple of things just to finish off here. So we know that solids increase in solubility when we increase the temperature. So when you warm up your water or something like that, we can add salt and we can dissolve more salt in boiling water than we would be able to in room temperature water, for example, which is important for cooking. The liquids don't really have an overall trend. It really depends on the liquid there, so you don't need to worry about them too much. As you can kind of see on the graph here, though, gases actually decrease in solubility when we increase the temperature. So if you want to dissolve a lot of gas in something, we want to cool down. The liquid, the solvent. You can see here though that the solubilities that we're looking here are really small. So we're talking milligrams per 100 grams. In the previous graphs, we were looking at like 30 grams of sodium chloride being dissolved per 100 grams. When we're looking at oxygen here, we're looking at 7 milligrams per 100 grams, and that's the highest value here. Looking at room temperature, and we're looking at below 4 milligrams per 100 grams. So that's a very small amount. So a couple of ramifications of this. One thing is that when you chill a drink, you can hold more gas in it. So this is useful if you've got a fizzy drink. Fizzy drinks don't actually have carbon dioxide on here, but carbon dioxide as a gas is going to be we're going to be able to dissolve more of it in something that's cold, which means that obviously the bubbles from a fizzy drink are coming from carbon dioxide. We can hold more fizziness in the drink if we keep it cold. If you heat up the drink, then all the carbon dioxide is going to come out of solution, bubble out, and then leave. So we want to keep our drinks cold if we want to keep carbon dioxide in them. It also has ramifications in terms of global warming. So as we increase the temperature, gases that are in the ocean, for example, we increase this temperature by a little bit, and we'll decrease the solubility of gases. So when we heat up the world, the ocean is able to hold less carbon dioxide, which releases it into the atmosphere, and then the carbon dioxide enhances the greenhouse effect, which will then lead to the temperature increasing, which will then lead to more carbon dioxide being released, and you can kind of see how this has a positive feedback loop of the released carbon dioxide causing more carbon dioxide to be released, which is not a good thing there. So we don't want to heat up the Earth for a multitude of reasons. One of the reasons is it's going to upset the gas balance in the ocean as well. All right, so you should be able to answer the chapter 14.2 questions as well, just from looking at the solubility curve, looking at the crystallization that's happening there, as well as solubility trends. So just as a reminder of the success criteria, you should remember how to use the solubility table from last time. You should be able to explain what the impact of changing in temperature is on the solubility of solids and gases. Remember, liquids are kind of a bit of a mixed bag. But solids, increasing temperature will always make the solubility go up. Increasing the temperature will make the solubility of a gas go down. There are a couple of exceptions. You might have seen one before on the graph there. But as a general trend, that's what we see. And you should be able to read a solubility curve and draw some conclusions about. You should be able to determine the solubility just from reading it straight off the graph. And you should be able to figure out whether a solution is saturated, unsaturated, or supersaturated from looking at that graph as well. All right, so have a go at those. Let me know if you've got any questions, and I'll see you next time.